y, you got a shorter version of differentiating. So that will be dy dx. But I believe most of you, this one, you now know it. It's equals to, remember here, there's a coefficient of 1. Then you multiply 4 times 1, that will be 4. You rewrite back x to the power of 4. Then you must always subtract 1, of which dy dx here, what will be, we're going to have 4x cubed. If they were to say do what? If they were to say find dy dx, so to say. Ne? And then let's try to do this one in first principle. Remember I told you to say whenever you are given a dy, whenever you're given y, there is the same as even if they were to say a given f of x, it's equals to x to the power of 4. So it means to say, even if you were to find this using first principle, to those who don't understand what is first principle, always when you use first principle, you must have f of x. It's equals to what? It's equals to x to the power of 4, as it is. And then now let's look at finding f of x plus h. Or this one, let me just leave it because I might be wasting time. But it's still one and the same thing. As long as you have understood me, how basically we do what we find, we differentiate, so to say, using first principle as well as the shorter version of that. Any question? So I think this one is not, it's not a what? It's not a trench smash. One thing that you need to understand is that the one that is a bit tricky is this one. If they can give you something like this, they say find dx of what? Of 12. You must have an understanding to say always when you differentiate 12, that is going to be 0. You know why? Because the derivative of a constant is 0. So I think on our next session from here going onwards, I'm going to show you how basically, why do we say the derivative always of a constant is 0? Because we were teaching you, or most of you were taught to say the derivative of a constant is always going to be 0. Mark, you might find that maybe most of you don't understand why do we say the derivative of a constant is 0. Ne? And then let's now continue, because this one is, it doesn't carry weight with regards to the marks in an exam. Now I'm just gonna concentrate on most important things that one needs to know. Ne? Any question before I proceed? So I showed you the theory of gradients. So we're gonna use the theory of gradients from here, hence going onwards, together with what I'm gonna teach you today with regards to graphs, theory of gradients. So for you to be able to master differential calculus, you must remember what I've showed you. I spoke about the theory of gradients, and then one thing that you need to understand with regards to this theory of gradients, we're having 4 graphs. Sorry, what tips do you have for me? Friday, I'm writing geometry. Geometry, just make sure that you have all, you master all the laws that I've just showed you, then you'll be good to go. So coming back to show Yakil. So coming back to what I'm saying here, this one is any line whereby is greater than 0. Any line that moves in that direction is going to be greater than 0. So when you say it's greater than 0, you know that it has a positive gradient. Then this one that moves like this, m is less than 0. Remember, m in math simply means gradient, especially in analytical geometry. Why am I showing you this? Is because of we are dealing with calculus. So the main aspect of us differentiating is to find the gradient. So when they say we are differentiating, we're finding the gradient or the slopeness of the graph or the steepness of the graph. That's why I come back to show you this theory of gradients, because it's the same. So one thing that you need to understand, any line that is parallel to the x-axis is gradient is what? Its gradient is 0. And then a line that's parallel to the y-axis its gradient is what? It's equals to undefined. Then, if you can master this, then there's no question that you want to understand. Any question? So you must know that now I'm introducing something that is very important. Please listen to me attentively. So this is a cubic function. I'm going to introduce cubic functions in calculus. One thing that is very, 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 very important is that cubic function, we are having two graphs, which are represented by this. Y is equals to ax cubed plus bx squared plus cx plus d. This is a Mother graph or a Mother equation of a cubic function. Not only that, we are also having another one, which can be written as y is equals to a into x minus x1, x minus x2, as well as x minus x3. So if they ask you to say write down the equation that best denotes a cubic function, you must tell them y is equals to ax cubed plus bx squared plus cx plus d. That is the Mother graph of a cubic function. Where one thing that is very important, you must know this. Always, it doesn't matter. Listen to me. Always, the value of a represents the shape of a cubic function. And then here, the value of d, it represents what we call the y-intercept. So when you speak about the y-intercept, it's a point on the graph where the graph passes on the y-axis. And then one thing that you need to understand, a cubic function, it has 3 x-intercepts. But that's not always the case. There are some instances whereby you can have a cubic function that has 1 x-intercept. There are some instances whereby you'll have a cubic function that has 2 x-intercepts. There are some instances whereby you'll have a cubic function that has 3 x-intercepts. What am I trying to say? Let me show you. But before I rush, let's consider working with the shape. So you have an understanding to say the shape here is represented by the letter A. And one thing that you need to understand, always, whenever you're given a cubic function that is like this, given in this equation, y is equals to ax cubed plus bx squared plus cx plus d. It means to say, when there are 2 instances that will happen. First instance is when you are having a being greater than 0. The second one is when you are having a is less than 0. Mind you, when I'm saying a is greater than 0, simply means to say what's going to happen. The value of a is positive. When I'm saying a is less than 0, it means the value of a is what is negative. What am I actually teaching here or say? Let me further elaborate. Make sure that if you're wise enough, make sure that you write notes, because what I'm explaining, some of you in class, you don't get an opportunity to be taught what I'm sharing with you. So when a is positive, always the graph of a cubic function in that equation is going to be like this. How do you see that? Look at this. When a is positive, you can draw a doll here. You know why? A is positive. When a is positive, the graph is a happy face. So it means to say, always, the second side, which is this one, this second side here, will always predict the shape of a cubic function. Can you see that it's a happy face here? It's happy. Why? Because it's positive. Why? Because a is greater than 0. Am I teaching or I'm playing? So that's the first thing. Then the next part, it's you understanding this to say, oh, this second part is the one that predicts the shape of the graph. If you're having a graph which is like that, now the second one, it's a is less than 0, which is negative. The graph is a frowning face. It means to say what's going to happen with regards to the shape. It means to say the shape will be looking downwards. You know why? Because of this. The sad face. So this one, happy face. This one is a sad face or frowning face. So that's one thing that you must have an understanding. So by just me teaching you these basics, there's no way you can struggle, even if I can give you an equation like this. If I can be happy enough to say, let's draw the graph of y is equals to x cubed plus 2x squared plus x, maybe minus 3. I'm just writing any equation that I'm just thinking in my mind. Just because of here, the coefficient is going to be 1. And this graph is written, and this graph is written in this equation. It means to say, Petulu, I'm going to write a doll tomorrow in the class so that I will break. When I Petulu, okay, it's cool. You can do that as long as you are being taught. So look at this. Here, the value of a is 1. You can all see. And then as long as the equation is like this, or given in this standard form, it means to say, if they say draw that graph, it's going to be this one. You know why? Because here the value of a is 1. 1 is positive. 1 is greater than 0. Hence, the graph that you must draw, it must be a happy face. Am I making sense? Any question?
Not
Any
yet,
question?
sir.
Yeah?
No, sir, not yet.
No, sir.
Do you all understand? Akwenga, do you understand? Okay. Asma, do you understand? They were saying yes. Okay, we can now continue since everyone seems like they understand. So that's the first thing. And then remember, I told you to say the cubic function can be written as that equation. But don't forget to say, the reason I'm saying, if it can be written in this form, in terms of the equation, and then they want you to draw the graph, it means to say it will be either graph number 1, which we consider being this one, or it will be, which we consider being this one, or it will be graph number 2, which we consider being that one. But if your graph, because that's not always going to be the case, I hope I'm loud. If your graph, it can be this one, y is equals to what? Ax cubed. Even here, the graph, it can be y is equals to ax cubed. In this case, the value of a here is greater than 0. In this case here, the value of a is less than 0. Look at how I wrote my equation. A typical example, let me make an example, a straightforward one. Y is equals to x
So,
cubed.
sir, can I ask,
Yes, you can
on
ask.
the second one, is it not supposed to be negative ax cube
Yeah, it's gonna
on
be
the
negative.
second part?
It's gonna be negative.
Oh,
Y is
okay.
equals to negative x cubed, because I've just tried to elaborate here to say a is less than 0. What is anything that is less than 0? Anything less than 0 is negative. That's why I wrote negative x cubed. So it means to say your graph will be only is the one that looks like a snake. Some of you have seen a what? An ugly graph like this. This one is gonna be like this. It's gonna be like this. Some of you have seen a graph like this. And then this one is gonna be like this. Some of you have also seen a graph which is like this. This is just a mere, yeah, it's kind of like a tan graph, yeah, kill. That's very true. So this one is the general equation, y is equal to x cubed. This one is general equation, y is equal to negative x cubed. I hope you are seeing how I'm writing them. So those are some of the things that you must know. We are done with regards to the shape. Any question?
No, sir.
Sure. Okay. To plot the graph, you must have the following. They will give you the equation sharp. Number one, you must know the shape based on what I've showed you. Number two, you must know my x-intercepts. Now here, that's where most of you will be caught. Because you have an understanding to say, Mara, a cubic function, it has 3x-intercept. But allow me to tell you that there are times whereby you'll get a cubic function that has 1x-intercept, having a cubed in the equation. I'm confusing you, ne? Okay, you will see. There are times whereby the cubic function can have 1x-intercept. There are times whereby the cubic function can have 2x-intercept. There are times whereby the cubic function can have 3x-intercept. What am I trying to say? A cubic function always, because of x cubed, it must have 3x-intercepts. But in an instance whereby it is having a 1x-intercept, that is a scenario whereby maybe our x-intercept is x is equals to 0, x is equals to 0, x is equals to 0. In that regard, it will have 1x-intercept. Okay, the times whereby it will have 2x-intercept. What am I trying to say? It can be x is equals to 1, x is equals to 4, x is equals to 4. It means to say x equals to 1, in that regard, it will act as an x-intercept. X is equals to 4, it will act as an x-intercept. The other one, it will act as the x value of the turning point where the graph will turn. What am I trying to say? You'll see. I'm going to explain just now. So number 3, you must have a y-intercept. Number 4, you must have a turning point. Number 5, you must have what we call the point of inflection. It is very easy, guys. Point of inflection. It's very easy. So now let me go back to what I was just trying to explain, because maybe some of you, I feel it in my spirit that most of you are actually maybe confused. I'm going to draw 3 Cartesian plane to support what I'm just trying to say here. So the first diagram, it's a cubic function that has only one x-intercept. Look at that. X is equals to 0, x is equals to 0, x is equals to 0. Just like that. So our equation here is going to be y is equals to x cubed. Sharp. And then with regards to this one, how best can I write that? This one, let me just write it like this. Yeah. I'm just picking. So look at this one. It touched here. It also touches there. I hope you're listening. I hope you're learning. So look at this graph. It touches here. And then as well as it touches there. So it means to say in this regard, you'll have one x value, which is less than 0. Another x value, which is going to be less than 0. As well another x value that is going to be greater than 0. And then in this regard, it simply means to say these x values, they must be the same. You know why? Because they touch here at this point. So it means to say on that particular turning point, if it's -1, it will be x equals to -1 as well as x equals to -1. And then if this is 1, this is -1 here. It means to say your x-intercept azoba x equals to -1, x equals to -1 as well as x is equals to 1. So that is a typical example whereby you are having a cubic function that has two x-intercepts. Actually, that three, but one is the same. Hence, when you look at the graph, it touches twice. And then you'll have another instance whereby you're having a mere straight one whereby you're having three x-intercepts which are actually different. So that is a graph that is going to be like this. Look at this one. It touches here. It touches there. It touches here. Touches there. As well as it touches there. But one thing that you need to understand, all of these are my cubic function. So with regards to the shape, I've just explained now. And then the catchy part, it will be here. Most of you will struggle with regards to finding my x-intercept. But if you stick with me when I'm teaching you, you're not going to struggle after we are done with calculus. What am I showing you? There are many ways in which you can find my x-intercept of a cubic function. So we use what you call the factor and the remainder theorem. Most of you know it. Or for you to find my x-intercept of a cubic function, because that's the one that is very tricky, we use long division method. Most of you are running away from long division method because maybe you don't know how to find long division or how to use long division method. But it's very easy, don't stress. Here, this is the tricky part. The rest is very easy. Yeah, just a second. And then when you
Instead of long division, can I use synthetic division?
Yeah, you can use any method. Synthetic is still correct. Now I use inspection. Synthetic, no. There are many ways, guys. I know 4 methods of finding a x-intercept of a cubic function myself that I taught myself. Ne? Let me show you. You know, that's why when I teach, I understand that the level of our IQ is not the same. But I'm going to teach you all the method. Ne? Number 1, you can use synthetic method. That is the one that most of your teachers are teaching because it's very easy. It's okay. And then you can use also long division method. That is the one that I like using. I'm going to show you, don't worry, I'm going to show you the simplest method on how to understand the long division method. And then the easiest of them all, most of you, you don't know it. It's what we call the K method. I doubt there is someone who knows it. Amongst the, we are 13 here on the session. You might find that the rest of you don't know the K method, of which K method is the easiest of them all. You are not going to struggle. You'll never find teachers teaching K method because it's a bit tricky there and there, but it's very easy. You know, even if a learner is a level 1 student, I can be able to teach a K method in a session. That learner will never ever forget or get wrong answers with regards to finding our x-intercept. That's the easiest of them all. You'll see it. And another thing, x-intercept will always say let y equals to 0. Y-intercept will always say let x equals to 0. Another thing, you know, in maths, there are questions which you can't get wrong, like this one. I still fail to understand why people, they get wrong answers when they say y-intercept. You know why? Because they will give you an equation like this. Let's say they give you, for peace sake, y is equals to x cubed plus 3x, maybe minus 4, for an example. If you go back to what I was teaching you, let me show you, because some of you will say, I say you never taught us. Myself, I'm one person who will show you many notes. I will show you so that I'm more safe to say I've taught you. Look at this. Y is always given. Yes, very true, one day. Y is always given. That's why I'm telling you this. This value of D, I told you to say it's the y-intercept. If you were listening to me, correct. And then when they say find the y-intercept, there's no way you can fail this because they will give you that value of D on the equation. Unless if maybe they draw an equation and then they want you to find the equation. Then it's a tricky one, but it's very easy as well. So in an instance whereby I give you this equation and I say, let's find my y-intercept, you can't tell me that you don't know the y-intercept because it's very easy. This -4, in this case, it represents the y-intercept. You know, in maths, there are many questions There are such questions which I can't expect you to get wrong, like this one. You know why? That -4, you understand that it represents the value of d. That's going to be the y-intercept. Why? Because when you want to find our y-intercept, we normally like to say y-intercept, let x is equals to 0. It means to say where there is x, that will be 0. Look at this. That will be 0 cubed. There's such questions in maths you can't expect to get wrong. Plus, remember, y-intercept, we normally say let x is equals to 0. And then you will be left with 4. Whether you are calculating it, whether you are not calculating it, the fact still remains to say your answer will be y is equals to -4. Why am I calculating here? I'm just showing you for those ones who like to calculate. But say, do you also have range and domain in this topic? Yes, you have range and domain. They will ask you, they will never leave you. As long as it's a function, you'll get range and domain. Don't worry, you are still going to do that. You see? So that's what I'm saying. There are such questions in math which you can't expect to get wrong answers. You know why? Like this one. If they say find the y-intercept, there's no need of calculating. You just go to the equation, you check -4 represents a y-intercept, just like that. And then with regards to the what? With regards to the turning point, how do you get the turning point of a cubic function? We normally derive ones. When we derive or differentiate ones, we find the turning point. And then that's how basically it is. The turning point of a cubic function is going to be two answers. You know why? Let me show you. Let me teach you maths. Angry, you are going to have a cubic function. Each and every time you are given a cubic function, when you differentiate it, it gives you a parabola or a quadratic function. Each and every time you are given a parabola or a quadratic function, you differentiate it, it will give you a straight line graph. It means to say you are always going to be given a cubic function as in terms of x cubed. When you differentiate it, it will give you a parabola. A parabola, you understand that it has two x-intercept. What is the main aspect of us having two x-intercept? It's because of when we differentiate the cubic function, then it gives us the equation of a parabola. It means to say we are finding turning points. You know why? When you go back to your graphs, your turning points with regards to a cubic function, it's a type of a graph that has two x-intercepts. It means to say it will have two turning points. It will turn there, it will as well turn there. You know why? Because we were given a cubic function, we differentiated it to find the turning point, because there's no way you can find the turning point of a cubic function without differentiating. Hence, you differentiate the cubic function, you'll get the parabola. That's why you are ending up having two x-intercept. You know why? Because the turning point of a cubic function, it has two x values. That's one thing that you need to understand. And then lastly, there are two ways in which you can find the point of inflection. Where do we use the form? I don't understand you when you say where do you use the
formula, sir. I meant formula.
Which formula?
The one of calculating the turning point.
Where do you use it? Yeah, it's a must. You'll use it. There's no formula that basically you can use. You differentiate, then you factorize, because when you differentiate the cubic function, it will give you a quadratic form, as in like x squared is equals to something. Then you factorize, or you use or I think maybe now I'm answering you. You factorize, or you use what do you call a quadratic formula. You're still gonna be correct. I think maybe that's what you were actually asking. And then with regards to the point of inflection, there are two ways in which you can find the point of inflection. Number one, let me show you what is a point of inflection, because maybe some of you don't understand what is a point of inflection. Whenever you have a cubic function like this, the point of inflection is the distance between the x values of the two turning points. What am I trying to say? Here is going to be your turning point, sharp. Let me just abbreviate it as TP1, where we say is turning point number 1. This one, it will be TP number 2, which is turning point number 2. So when I speak about the point of inflection, it's the average distance between the x values of our turning point. This value right here, we call it the point of inflection. Don't abbreviate it. Write it in full. I'm just saying point of inflection so as to save time. And then with regards to finding the point of inflection, It means to say you'll use the second derivative. It means to say you'll take the equation of a cubic function, you differentiate it. It will give you a parabola. You take the equation of a parabola, you differentiate it. It will give you a linear function. A linear function has one x value. It means to say also the point of inflection, you'll only have one x value of the point of inflection. After getting that x value, you take that x value, you substitute it back to the original equation. It will give you the respective y value that is associated to that point of inflection. That is the first concept of you making sure that you do what? You find the point of inflection. Let me repeat what I've just said. The point of inflection, you find it by using the second derivative. You're going to derive twice. It will give you the second, it will give you the point of inflection. Or you add the x values of the turning points, you divide by 2. That's another method of finding the point of inflection. Point of inflection. The formula, it will be 𝗚𝗃𝗃1 plus 𝗚𝗃𝗃2. You all divide by 2, which is the average. You're going to take the x value of turning point number 1, you add the x value of the turning point number 2, you divide it, then it gives you here, which is the mid average. Am I making sense? Hello, guys. Hello. Are you still with me?
So, sir, what you basically you were saying here is that the point of inflation it's where the graph changes its sign, or
That's not where the graph changes its sign. That is just the point of inflection. That is the average distances between the x values of the turning point. That's always going to be the point of inflection.
so our gradient is zero. Actually, not zero, but it's
Positive. It's going to be positive
okay.
gradient. You know why? I'm not guessing. Let me teach you, mates. Yeah, it's good to ask. And thank you, 𝗏𝗍𝗃, for asking so many questions. I want people who ask. I prefer that when I teach, people are asking. It goes back to the theory of gradients. Let me now go back. Because maybe some of you might be taking what I'm teaching, but not all of you. Some people, when you teach, they will be like, maybe it's not going to help us. But there's a reason why I'm writing all these notes. Let me show you. I want to go back to the theory of gradients. And then people will be able to say, Mara, what says teaching is very important. Now, look at those 4 graphs. If you can understand those 4 graphs of the theory of gradients, then there's no question that we'll get wrong in calculus. Ne? Now let's go back to the point of inflection to support my statement. So I've just said here, the point of inflection, we're going to have what? We're going to have, let me check. I said we're going to have a positive gradient. There's a reason why I'm saying that. When you look at that dot where I've just made the point of inflection, let me try to introduce a tangent. What's going to happen? It means to say I'm going to have a tangent that moves like that. Do you see? So this straight line, it touches the curve at that point of inflection. Look at it. This is a line that moves like that. This is the line that moves like that. Any line that moves, this is the line that moves like that. So to say, any line that moves like that, what am I trying to say? It has a positive gradient. So it means to say here, we are having what? We are having a positive gradient, just like that. Did I answer you, Wandile? That's why I've tried to explain to say the main aspect of us differentiating is to find the gradient.
Yes, you've answered me. Say, right now, I've just realized that definitions are way more important in maths too. It's not only in physics.
Thank you. Sure. So with regards to that, now, thank you, Wandile, for introducing that. Let me now show you. One thing that you need to understand. I'm trying to draw a graph here. So, at the turning point, look at this. We're having a line that is like that. At the turning point, we're having a straight line that is like that. So those 2 yellow straight line graphs on the turning points. Then here we're having this one. And then here we are having, let me put the red one. A red one right there. Let me put a blue one. So when you go back to the theory of gradients, and when we differentiate, we say at any turning point, dy dx is equals to 0. It's because of the gradient here. It's equals to 0. You know why? If you can put the Cartesian plane, that line will be parallel to the x-axis. Any line that is parallel to the x-axis is gradient, it's 0. That's why we say on the turning points, you're going to have a gradient that is 0. Because even if you put a straight line graph, you're going to have a gradient that is less than 0. Look at this one. The gradient is less than 0. It's decreasing. Look at this one here. The gradient is increasing. It's greater than 0. Look at this one. The gradient is what? It's less than 0. All of these straight lines graph that I've just drawn on top of this cubic function, it traces you, or it goes back to the theory of gradients. Am I making sense? Compare all those straight lines that I've just wrote on the cubic function together with the theory of gradients. You'll get to understand what I'm trying to